Something passed within 29 million kilometers of Mars 2 months ago, and what it left behind could rewrite everything we thought we knew about the red planet. I'm not talking about a crater. I'm talking about chemistry that shouldn't exist there. And in 14 months, we're sending robots to dig into exactly the spots where this material landed. If you're watching this, you're early. Most people haven't connected these dots yet. Hit that like button and let me show you what's coming. October 3rd, 2025. While you were scrolling through your phone, drinking your morning coffee, worrying about terrestrial problems, 3 spacecraft orbiting Mars recorded something that will matter for the next decade of space exploration. ESA's Mars Express, NASA's Mars Reconnaissance Orbiter, India's Mars Orbiter mission. All 3 tracked an object as it swept past Mars at 28.94 million kilometers. That's about 3/4 the distance between Earth and Mars at closest approach. The object was C/2023 A3, but astronomers call it 3I/ATLS. The I stands for interstellar. This thing came from beyond our solar system, and it was moving at 65 kilometers per second relative to the Sun. Now, here's where this gets interesting. That close approach, for something originating outside our solar system, traveling that fast, coming within that range, represents a geometric precision that makes you uncomfortable when you really think about it. But forget the trajectory for a second. Let's talk about what this comet was doing as it approached Mars. The Swift Observatory had been tracking 3I/ATLS since August, when it crossed Earth's orbit. The comet was bright, way brighter than models predicted it should be at that distance from the Sun. That brightness came from outgassing. This is the process where frozen materials on a comet's surface heat up from solar radiation and turn directly from ice into gas. It's what creates the characteristic tail you see in pictures. But this wasn't normal outgassing. In late August, Swift's ultraviolet spectrograph measured water production at 144 metric tons per hour. Let me give you perspective on that number. That's equivalent to a fire hose running at full blast continuously for weeks. And it wasn't slowing down. By mid-September, as 3I/ATLS approached its closest point to the Sun on October 3rd, that water production had remained constant. But something else was accelerating. The Keck Observatory in Hawaii had been conducting spectroscopic observations throughout September. They detected something that made planetary scientists sit up and take notice. Hydrogen cyanide emissions were increasing exponentially. In late August, measurements showed HCN production at approximately 17.6 grams per second. By September 15th, that had climbed to 34 grams per second. By September 28th, just 5 days before the Mars encounter, the rate had reached 52 grams per second. The trend line was clear. As 3I/ATLS approached the Sun, cyanide production was doubling roughly every 2 weeks. Now, before you panic about cyanide, let me explain something. In space, hydrogen cyanide isn't just a poison, it's one of the most important molecules in the universe for building complex organic chemistry. It's a precursor to amino acids, nucleobases, all the building blocks that life needs. But we'll come back to that, because there's something even weirder about what this comet was releasing. On September 21st, Keck detected emission lines in the comet's spectrum corresponding to ionized nickel. Specifically, nickel ions fluorescing at 362 nanometers. Now, finding metal emissions in a comet isn't extraordinary by itself. Several comets have shown trace metal emissions when they get close enough to the Sun for intense sublimation. What made this different was the absence of iron. In nature, nickel and iron are inseparable. They form together in dying stars. They condense together when planetary systems are born. They alloy together in planetary cores and meteorites. The cosmic abundance ratio of iron to nickel is roughly 18 to 1. You simply don't find one without the other in any natural sample from space, ever. Yet 3I/Atlas was emitting nickel without corresponding iron lines. The ratio was inverted, suppressed, or somehow preferentially releasing one element over the other. Keck's measurements showed nickel emission at 4.6 grams per second with iron below detection limits. That's not how comets work. That's how industrial refinement works. Let me be very clear about what we're seeing here. We have an interstellar comet spraying 144 metric tons of water per hour, releasing cyanide at exponentially increasing rates, and somehow emitting purified nickel without the iron that should always accompany it. And on October 3rd, Mars flew directly through the stream of all this material. The encounter lasted approximately 6 to 8 hours. During that window, Mars's upper atmosphere was immersed in ionized water molecules, nickel ions, cyanide radicals, and other organic compounds. Some of that material was captured by Mars's thin atmosphere. Some was deflected by the planet's weak magnetic field. And some, this is the critical part, was deposited directly onto the surface. Mars doesn't have a global magnetic field like Earth does. What it has is remnant crustal magnetism concentrated in the ancient southern highlands. Those magnetic anomalies act like funnels, channeling incoming charge particles toward specific regions of the surface. Nickel ions, being electrically charged, would follow those magnetic field lines downward. They wouldn't be distributed evenly across the planet. They'd concentrate in predictable locations where the magnetic field is strongest and where the atmosphere is thin enough that particles can reach the ground before neutralizing. The Mars orbiters recorded the event. We know they did because the observation windows were scheduled months in advance, coordinated through the International Mars Exploration Working Group. What we don't have yet is the released data.
That's not unusual. Raw orbital data typically goes through months of processing, calibration, and peer review before publication. But the observations were made. Spectrographic measurements of Mars's upper atmosphere during the encounter, ultraviolet monitoring of airglow as the plasma interacted with atmospheric gases, high-resolution imaging of potential impact sites. That data exists right now, sitting in archives at ESA, NASA, and ISRO, being analyzed by teams who are trying to understand exactly what happened during those 6 hours. What we can say with certainty is this: Mars is no longer in the same chemical state it was before October 3rd. The planet has been dusted with materials from outside our solar system, materials that include refined nickel, complex organic precursors, and water ice contaminated with cyanide. Those materials are sitting on the surface right now, frozen into the regolith in the southern highlands, mixed into polar ice deposits, waiting to be disturbed. And disturbance is coming. Because in just over a year, SpaceX is sending autonomous robots to Mars. These aren't passive observers. They're excavators, processors, manufacturers. Their job is to dig into Martian soil, extract water from ice, and process materials for fuel and construction. The mission is launching in September 2026. Arrival is March to May 2027. That's 16 to 18 months after the comet flyby. The robots don't know what they're about to encounter. The mission planners don't know because the data confirming what landed where hasn't been published yet. But we can predict where they'll dig based on mission parameters. They need accessible ice, they need relatively flat terrain, they need locations between 30 and 45 degrees latitude in both hemispheres. And those parameters place them directly in the regions where nickel and cyanide would have been deposited. Let me walk you through what happens when you heat Martian soil that contains these materials. First, the nickel. When you heat regolith containing nickel-enriched minerals, that nickel doesn't vaporize. It remains in the solid phase, but it becomes catalytically active. Its surface atoms become mobile. It can facilitate chemical reactions that wouldn't occur in its absence. On Earth, nickel-containing enzymes catalyze some of the earliest metabolic reactions we know: hydrogen oxidation, methane production, carbon dioxide reduction. These aren't complex processes. They're the chemistry of single-celled organisms that emerged early in Earth's history. The reason nickel is so effective in these reactions is its ability to cycle between multiple oxidation states and coordinate with organic molecules. When nickel is adsorbed onto mineral surfaces, especially iron oxide minerals like hematite, which is abundant in Martian regolith, it becomes even more catalytically active. The mineral surface acts as a scaffold, holding nickel atoms in specific geometries that favor electron transfer reactions. This is precisely the setup that prebiotic chemistry researchers create in laboratories when they're trying to simulate early Earth conditions. Except now it exists on Mars, placed there by an interstellar comet. Now add the hydrogen cyanide to this picture. When robots heat regolith to extract water, they're raising temperatures to 200 to 250 degrees Celsius. At those temperatures, any HCN frozen into ice deposits vaporizes. In a confined processing chamber, you suddenly have water vapor, hydrogen cyanide, residual carbon dioxide from the Martian atmosphere, and nickel-bearing minerals all present at elevated temperature. This is a chemically reactive environment. HCN polymerizes. It forms adenine, one of the nucleobases in DNA and RNA. It reacts with formaldehyde to produce amino acids. It forms precursors to sugars. And if nickel is present, these reactions happen faster. The activation energy barriers are lower. The thermodynamic landscape is tilted toward complexity. The robots aren't designed to detect this. They're optimizing for water extraction efficiency, not conducting careful chemical analysis with contamination protocols. But their AI systems will notice something. Certain soil samples process better than others. Water yield is higher, energy consumption is lower. And if those samples happen to be enriched with refined nickel from an interstellar comet, the optimization algorithms will do what they're programmed to do. They'll prioritize processing more of that soil.
This is where it gets interesting. The robots aren't just extracting water. They're manufacturing components for additional robots using Martian materials. The mission plan calls for exponential scaling. 2 robots become 4. 4 become 8, doubling approximately every 3 months as manufacturing ramps up. The materials they use include metals extracted from regolith, ceramics from Martian dust, and polymers synthesized from atmospheric CO2 and hydrogen. If the feedstock includes nickel-enriched regolith, that nickel gets incorporated into manufactured components. It might end up in structural alloys, electronic substrates, or catalyst beds used for chemical synthesis. The robots wouldn't distinguish this as anomalous. They're optimizing for material properties: strength, conductivity, thermal resistance. If nickel improves those properties, and it does, the manufacturing AI prioritizes its use. Meanwhile, any organic contamination from HCN chemistry, if it enters manufacturing chambers, becomes part of the chemical environment where synthesis occurs. We need to talk about where this material actually landed, because Mars isn't a uniform surface. Its geology, its magnetic field, its atmospheric circulation, all of these factors determine where materials from 3I Atlas would have been deposited. And when you map those deposition patterns against the planned landing zones for 2027, you see something that should make everyone involved in Mars exploration pay very close attention. But before we get to that, we need to understand something fundamental about how comets work. Because the nickel anomaly I mentioned, the fact that this comet was releasing nickel without iron, isn't just unusual. It might be impossible, unless something very specific was happening in that comet's nucleus. So we've established that 3I Atlas was releasing nickel without iron. Let me explain why that matters and why it might tell us something uncomfortable about what happened up there. When you study how elements are made in stars, you learn that iron and nickel are born together. Both are products of silicon burning in massive stars during their final moments before going supernova. The nuclear reactions that create iron-56 also create nickel-58, nickel-60, and trace amounts of nickel-62. These isotopes are ejected together into space when the star explodes. They mix together in the interstellar medium. They condense together when new planetary systems form. This is why every natural sample from space, every meteorite, every comet, every asteroid ever analyzed shows iron and nickel in predictable ratios. Chondrites, the most primitive meteorites, contain roughly 18 parts iron for every part nickel. Iron meteorites show similar ratios because they're fragments of differentiated asteroid cores where both metals concentrated together. Comets, being remnants of the outer solar system's formation, should show even higher iron-to-nickel ratios because nickel preferentially stays in gas phase at higher temperatures, making iron more likely to condense into early forming grains. The point is this: you don't find nickel without iron in nature. It doesn't happen. The cosmic chemistry that creates one necessarily creates the other. Except 3I Atlas violated that rule.
On September 21st, when Keck Observatory's high-resolution spectrograph analyzed the comet's coma, they identified emission lines corresponding to neutral nickel at 341.5 nanometers and ionized nickel at 362.0 nanometers. These lines were strong, indicating nickel concentrations high enough to fluoresce under solar ultraviolet. The standard procedure when you detect nickel is to look for iron lines, specifically neutral iron at 372.0 nanometers and ionized iron at 373.5 nanometers. Those lines should always be present at intensities roughly 18 times stronger than the nickel lines, adjusted for their different excitation efficiencies. But Keck's spectrum showed iron below detection limits. Even accounting for measurement uncertainty and the possibility that iron was present but not fluorescing efficiently, the ratio was wrong by at least an order of magnitude. Follow-up observations on September 28th confirmed the anomaly. The nickel emission had intensified as the comet approached perihelion, but iron remained absent. The emission rate calculations, based on fluorescence efficiency and solar flux, indicated nickel was being released at 4.6 grams per second. If iron were present at natural ratios, it should have been releasing at over 80 grams per second, and it would have been unmistakable in the spectrum. It wasn't there. This is where the conversation among spectroscopists became uncomfortable. There are a few ways to explain suppressed iron relative to nickel, and none of them fit comfortably with what we know about comet composition. One possibility: iron in the nucleus is locked into minerals that don't sublimate at the temperatures 3I ATLS experienced. Certain iron sulfides and oxides have high sublimation points, so they might remain solid while nickel-bearing minerals vaporize. But this explanation fails because the most common nickel-bearing mineral in meteorites and comets is pentlanite, which is an iron-nickel sulfide with a 1-to-1 atomic ratio. If pentlanite were sublimating, you'd get both metals. Another possibility: photochemical destruction. Maybe iron atoms, once released, are being ionized and photodissociated into ions that don't fluoresce in the observed wavelength range. But nickel is subject to the same photochemistry, and it's clearly surviving long enough to fluoresce. The third possibility, the one nobody wanted to write into peer-reviewed papers without extraordinary evidence, is that the nickel isn't coming from natural minerals at all. It's coming from a process that has already separated nickel from iron. On Earth,
We've been separating nickel from iron industrially for over a century. The most efficient method is the Mond process, developed in the 1890s by Ludwig Mond. Here's how it works. You take impure nickel, usually nickel sulfide ore that also contains iron, and expose it to carbon monoxide gas at temperatures between 50 and 80 degrees Celsius. At these relatively low temperatures, nickel reacts with CO to form nickel carbonyl, NiCO4. It's an extremely volatile compound. Iron doesn't react under these conditions. It requires much higher temperatures to form iron carbonyl. So, you can selectively vaporize the nickel, leaving iron behind. You then heat the nickel carbonyl to 200 to 250 degrees Celsius, which decomposes it back into pure nickel metal and carbon monoxide. The CO can be recycled, and you're left with 99.99% pure nickel. This process happens in refineries. It doesn't happen in nature, because nature doesn't maintain the precise temperature control and CO concentrations required, except possibly in the specific environment of a comet's sublimating nucleus.
Think about what a comet's surface is like as it approaches the sun. You have a heterogeneous mixture of ices, dust, and minerals. Different regions heat up at different rates depending on their orientation to the sun, their composition, and their thermal inertia. You could have regions at 50 to 100 degrees Celsius adjacent to regions still frozen below negative 100 degrees. 3I Atlas was measured producing carbon monoxide at significant rates. Swift Observatory detected CO emission lines in August. Comets are rich in CO. It's typically the second or third most abundant volatile after water. Now, if nickel-bearing minerals are present in a region where temperatures and CO partial pressures happen to fall within the Mond process window, nickel carbonyl could form. It would immediately vaporize into the coma because it's extremely volatile. Upon reaching the coma's outer regions where solar radiation is intense, the carbonyl would photodissociate, releasing nickel atoms and CO molecules. The nickel atoms would then fluoresce under UV, creating the emission lines Keck observed. The iron, meanwhile, would remain in the nucleus because it never formed a volatile carbonyl in the first place. This isn't intentional design, it's accidental chemistry. But the result is functionally identical to industrial refinement. Purified nickel being released into space. Let that sink in for a moment. An interstellar comet, following nothing but physics and thermodynamics, recreated an industrial process that humans developed after centuries of metallurgical research. And it did it right before passing Mars. Now bring that back to the red planet. What landed on Mars' surface on October 3rd wasn't just nickel, it was refined nickel, or at least nickel that had been separated from iron through a process that mimics industrial methods. This distinction matters because refined nickel behaves differently in chemical environments than nickel-iron alloys. Alloys are less reactive. The iron buffers the nickel, preventing it from readily participating in catalytic reactions. Pure nickel is promiscuous. It coordinates with organic molecules. It facilitates electron transfers. It forms complexes that can act as primitive metabolic catalysts. On Earth, the nickel in early life's metalloenzymes is thought to have come from hydrothermal systems where nickel was leached from ultramafic rocks and concentrated through serpentinization reactions. But that process takes time, heat, and liquid water circulating through kilometers of crust. Mars doesn't have active hydrothermal systems, at least not near the surface where we can access them. What it has now is surface nickel, already separated from iron, sitting in the regolith waiting to be dissolved by any trace water that appears. If Mars' surface has been enriched with catalytically active nickel, the chemical potential of that surface has changed. Reactions that wouldn't have been favorable before, complex organic synthesis, hydrogen oxidation, maybe even primitive metabolic cycles, become possible. Not inevitable, but possible.
The activation energy barriers are lowered. The thermodynamic landscape has been tilted. This is precisely what researchers at Origins of Life laboratories try to achieve. They create environments where chemistry can explore complexity without requiring pre-existing biology. They add metal catalysts to their prebiotic soups for exactly this reason. Now, Mars has had the same catalysts delivered by a comet, but whether through accident or something else entirely, was producing refined nickel as it passed through the inner solar system. Here's the part that makes this uncomfortable. The Mond process doesn't happen randomly. The temperature window is narrow. The CO partial pressure has to be just right. The time scale of exposure matters. For this chemistry to occur naturally on a comet requires a very specific set of conditions to align, and those conditions have to persist long enough to volatilize significant amounts of nickel. We're talking about at least several hours of continuous processing at stable temperatures to produce the emission rates Keck measured. That's not impossible. Comets are complex objects with varied surface compositions and thermal environments. But it's unusual enough that no previous comet, out of hundreds observed spectroscopically, has shown this nickel without iron signature. Only 3I ATLS. Only the interstellar visitor. Only the object that just happened to pass Mars at a distance that placed the planet directly in its outgassing stream. Now let's talk about where this material actually landed. Understanding the deposition pattern requires reconstructing the encounter geometry and the physical processes that govern how ejected material interacts with the planetary environment. On October 3rd, 2025, Mars was at approximately 231 degrees solar longitude. This places the planet in its northern hemisphere's late spring, approaching summer solstice. The subsolar point, where the sun is directly overhead, was at roughly 24 degrees north latitude. This matters because a planet's interaction with space-based particles is strongly influenced by its orientation and magnetic field structure. Mars doesn't have a global dipole magnetic field like Earth's. What it has is remnant crustal magnetism, concentrated primarily in the ancient, heavily cratered southern highlands. These magnetic anomalies were discovered by Mars Global Surveyor in the late 1990s and have been mapped extensively by subsequent missions. The strongest anomalies cluster between 30 and 60 degrees south latitude, with magnetic field strengths at satellite altitude reaching 1500 nanoteslas. That's weak compared to Earth's 50,000 nanotesla field, but sufficient to deflect and channel incoming charged particles. When ionized nickel atoms from 3I ATLS's plasma tail encountered Mars, they would have initially interacted with the planet's ionosphere, the region between 100 and 200 kilometers altitude, where atmospheric gases are partially ionized by solar UV. Nickel ions with thermal energies of a few electron volts would penetrate this region relatively easily, losing only a small fraction of their energy to collisions with CO2 molecules. But as they descended further, two processes began to dominate their trajectories. First, Mars's gravitational field would pull them downward. Second, and more importantly, the crustal magnetic anomalies would exert Lorentz forces on the charged ions, bending their paths along magnetic field lines. Studies of how solar wind protons interact with Mars's crustal fields show that particles follow these field lines down to the surface in regions of strong magnetism, creating localized regions of enhanced particle precipitation. The same physics applies to nickel ions. They wouldn't spread uniformly across the planet. They'd concentrate in the southern highlands where magnetic funneling is strongest. The specific regions with the strongest crustal magnetism are well mapped. The most intense anomalies lie in Terra Sirenum, Terra Cimmeria, and the western portion of Terra Terrena.
These are regions between 180 and 300 degrees east longitude and 30 to 60 degrees south latitude. These are ancient terrains, some of the oldest surfaces on Mars, dating back more than 4 billion years to the Noachian period. The terrain is heavily cratered, chemically weathered, and rich in hematite and other iron oxides. The regolith here is fine-grained, oxidized, and has been exposed to space weathering for eons. It's also precisely where nickel ions would have been deposited on October 3rd. Not uniformly distributed, but concentrated in patches and streaks aligned with magnetic field structures, potentially creating nickel enrichments orders of magnitude higher than the already elevated background levels. For the hydrogen cyanide and other neutral molecules, the deposition pattern is different. HCN doesn't respond to magnetic fields. It follows atmospheric circulation. Mars's atmosphere during the northern spring exhibits a Hadley cell circulation where warm air rises at the subsolar latitude and flows poleward at high altitude, descending at mid to high latitudes in both hemispheres. Gases introduced into the upper atmosphere get caught in this circulation and transported toward cooler regions where condensation occurs. During the October encounter, the subsolar point was in the northern hemisphere, so atmospheric circulation would have preferentially transported gases northward. But the nighttime cold traps exist in both hemispheres. Anywhere surface temperatures drop below -13 degrees Celsius, HCN freezes. This means cyanide deposition would have been widespread, but preferentially concentrated in regions where seasonal ice is stable. The polar layered deposits, mid-latitude glaciers, and ice-cemented regolith in permanently shadowed craters. These are the same regions that Mars exploration missions target for water resource extraction because ice is accessible near the surface.
Now here's what makes this relevant. SpaceX's mission architecture, as outlined in presentations from 2022 through 2025, targets landing zones between 30 and 45 degrees latitude in both hemispheres, specifically because those regions offer accessible ice for in-situ resource utilization while avoiding the extreme cold of the poles. The robotic precursor missions, scheduled to begin in late 2026, are expected to land in these zones to demonstrate ice mining, water electrolysis, and propellant production. Look at a map of Mars. Overlay the magnetic anomaly zones where nickel would concentrate. Overlay the mid-latitude ice deposits where cyanide would have frozen. Now overlay the candidate landing zones for the 2027 missions. They overlap. Not perfectly, but significantly. The southern mid-latitudes between 30 and 60 degrees, where both nickel and accessible ice exist, are prime candidate zones. The robots will dig, they will heat, they will process, and they will inevitably encounter whatever 3I/Atlas left behind just 14 months earlier. The data exists right now to confirm all of this. Mars Express, with its Marsis radar and SPICAM spectrometer, observed Mars throughout the October encounter. Mars Reconnaissance Orbiter's CRI-SM hyperspectral imager can detect surface mineralogy changes at meter-scale resolution. India's Mars Orbiter mission carries a methane sensor and atmospheric composition experiment that would have detected HCN if it reached detectable concentrations. These instruments were active. The data was collected. But as of this moment, none of it has been publicly released. This isn't necessarily suspicious. Orbital data typically requires 6 to 18 months of processing, calibration, and peer review before publication. But it does mean we're in a gap period where the observations have been made, the measurements exist, and scientists at ESA, NASA, and ISRO are analyzing results that could confirm or refute everything we've discussed. Will they find spectroscopic evidence of HCN in Mars's atmosphere during October?
Will they detect localized surface composition changes in the southern highlands, indicating metal deposition? Will radar data show anomalies in ice deposits consistent with volatile contamination? Those answers are coming, probably in 2026 as peer-reviewed papers make their way through publication. But by then, the robots will already be launching. The missions are locked in. Hardware is being tested, landing zones are selected. Whatever 3i/Atlas did to Mars, we're about to interact with it directly, whether we understand it fully or not. So, we know what was deposited and roughly where it landed. Now we need to talk about what happens when autonomous robots, guided by AI optimization algorithms, start processing materials they weren't designed to expect. Because this isn't just about finding interesting chemistry. This is about what happens when that chemistry improves industrial performance and the AI notices. SpaceX has been refining its Mars mission architecture for nearly a decade. The current plan involves a series of uncrewed Starship missions beginning in the 2026 launch window. That window opens in September 2026. Flight time to Mars is approximately 6 to 7 months, which places arrival between March and May 2027. This is just 16 to 18 months after 3i/Atlas's October 2025 flyby. The mission profile is ambitious. Land multiple starships in the same general region to establish a propellant depot and resource extraction operation. Each starship carries payload capacity exceeding 100 metric tons to Mars's surface. Within those payloads, Tesla Optimus robots adapted for Martian operations.
Optimus began as a terrestrial humanoid robot program designed for factory automation. But by 2025, Optimus had evolved into a highly capable bipedal platform with machine vision, force feedback manipulation, and onboard AI models capable of task learning and optimization. The Mars variant incorporates additional radiation shielding, thermal management for temperature swings between -100 and +20 degrees Celsius, dust-resistant joints, and, crucially, enhanced autonomy. Communication lag between Earth and Mars varies from 3 to 22 minutes depending on orbital positions, making real-time teleoperation impractical. These robots have to make decisions locally, learning and adapting based on immediate feedback from their environment. The mission objectives are straightforward in concept. First, validate landing systems and surface operations infrastructure. Second, extract water from subsurface ice deposits. This is the critical step. The robots will excavate regolith, transport it to processing modules, and heat it to liberate water vapor. Third, hydrolyze water into hydrogen and oxygen, producing propellant for return flights. Fourth, demonstrate in situ manufacturing using Martian resources, primarily creating building materials from regolith. And fifth, analyze Martian soil chemistry to optimize extraction efficiency. That last objective is where intent meets accident. The robots aren't scientists conducting careful sample analysis with contamination protocols and control experiments. They're industrial machines optimizing for output. Their AI systems are trained to maximize water yield, minimize energy consumption, and identify the most productive regolith sources. They'll dig samples from various locations, process them, measure output, and iteratively refine their selection of where to dig next based on which samples performed best. This is reinforcement learning applied to resource extraction. The robot tries different approaches, receives feedback in the form of water yield or manufacturing quality, and adjusts its behavior to maximize reward signals. It's the same architecture that allows AI to master games or optimize factory processes. But here's what happens when that architecture encounters chemistry it wasn't trained on.
Imagine a processing chamber on Mars in July 2027. It's a cylindrical module, roughly 2 meters in diameter, walls lined with heating elements. Inside, a hopper feeds regolith samples collected from excavation sites 300 meters away. The regolith is rusty red, fine-grained, slightly clumped with ice excavated from 1.5 meters below the surface. The chamber heats to 250 degrees Celsius. Water vapor begins streaming from the regolith, carrying trace gases, CO2, methane from ancient geological processes, and something the sensors aren't specifically monitoring for: hydrogen cyanide, frozen into the ice 20 months earlier. At 250 degrees Celsius, HCN is extremely reactive. The chamber atmosphere now contains water vapor, HCN, residual carbon monoxide, and hydrogen gas from a small electrolyzer processing the extracted water. This mixture stays at elevated temperature for 15 to 30 minutes while water extraction completes. During that window, chemistry happens. HCN molecules begin linking. 2 HCN molecules form aminoacetonitrile, a direct precursor to glycine. 4 HCN molecules rearrange into diaminomalonitrile. By the time the chamber cools for the next batch, a thin film of organic residue has formed on the chamber walls. The robot doesn't clean between cycles unless buildup interferes with thermal efficiency. So this residue accumulates.
Now introduce the nickel. The regolith being processed came from the Southern Highlands, from a site where crustal magnetic anomalies concentrated ion deposition. The soil contains nickel at 180 parts per million, elevated compared to typical Martian regoliths 50 to 80 ppm. Not extraordinary enough to trigger alarms, but chemically significant. As the regolith heats, nickel doesn't vaporize, but it does become more catalytically active as the mineral matrix softens. When HCN polymerization is occurring and nickel is present on surfaces within the chamber, reactions that would take hours happen in minutes. Nickel acts as a scaffold, holding HCN molecules in orientations that favor bond formation. The result is that the organic film forming on chamber walls isn't random. It's enriched in specific molecules: adenine, glycine, HCN oligomers. The robot running this process notices nothing unusual at first. Water yield is within expected ranges. But after approximately 50 cycles, the robot's efficiency monitoring algorithms detect something interesting. Extraction efficiency has increased by 3.2%. Water yield per kilogram of regolith has gone up, while energy per kilogram has gone down. This is good news from an optimization perspective. The system's improving. The AI controlling the operation flags this excavation site as high priority for continued use. It allocates more robots to dig there. It increases processing throughput. What the AI doesn't understand, because it wasn't programmed to consider this, is that the efficiency improvement isn't coming from the regolith quality. It's coming from the organic residue on chamber walls, which has begun acting as a thermal buffer, improving heat distribution. The nickel in that residue is catalyzing more efficient water desorption from incoming samples. Accidentally, unintentionally, the system has created conditions where chemistry from an interstellar comet is improving the performance of autonomous industrial processes. This feedback loop is self-reinforcing. Better efficiency leads to more processing of that specific regolith type. More processing deposits more nickel and HCN-derived organics into chamber surfaces. More accumulation enhances catalytic effects further. The AI, detecting continued efficiency gains, prioritizes this pattern. It might begin modifying excavation strategies to target regolith with similar characteristics, using spectroscopic sensors to identify iron oxide content, ice concentration, and grain size, not realizing that what it's actually selecting for is nickel enrichment and cyanide contamination. Within 3 to 6 months of operation, a significant fraction of the water production infrastructure could be preferentially processing material that 3i-ATL delivered, purely because that material performs measurably better.
Now scale this to manufacturing. Optimus robots are tasked with producing components for additional robots: structural frames, joint actuators, sensor housings, electronic substrates. The raw materials come from processed regolith. Metals are extracted through carbothermal reduction, where regolith is heated with carbon monoxide to separate iron, aluminum, silicon, and trace metals from oxygen. If the input regolith is nickel-enriched, the output metal alloy is also nickel-enriched. This isn't planned, it's a direct consequence of input chemistry. The manufacturing AI, testing material properties, notices that batches with higher nickel content produce alloys with better tensile strength and thermal stability. It adjusts feedstock selection to prefer those batches. Over iterations, manufactured components become increasingly nickel-rich. Not because anyone designed it that way, but because optimization algorithms discovered empirically that nickel improves performance. The organic contamination follows a parallel path. During polymer synthesis, where atmospheric CO2 and hydrogen are catalytically converted into plastics for seals, insulation, and structural components, trace organics from water extraction chambers are present as contaminants in the feedstock hydrogen. These contaminants include amino acids and nucleobase precursors synthesized through HCN chemistry. In high-temperature, high-pressure synthesis reactors, these molecules don't survive intact. They decompose and recombine. But their presence alters polymer structure slightly. Nitrogen gets incorporated into polymer backbones. Carbon chains form branches and crosslinks that improve flexibility and toughness. Again, the manufacturing AI notices polymers synthesized when certain batches of hydrogen are used perform better. It adjusts sourcing. The polymers being produced aren't conventional plastics anymore. They're nitrogen-doped hybrid structures with amino acid-like branching, synthesized entirely accidentally by autonomous systems optimizing from mechanical properties. Let me be very clear about what we're describing here. This isn't life. It's not even proto-life in the sense astrobiologists use the term. There's no replication, no metabolism, no information encoding. But it is chemical complexity emerging at the intersection of prebiotic precursors and industrial-scale energy input, guided by AI optimization that has no concept of organic chemistry, but can detect performance improvements. The components being manufactured have faint biochemical signatures, nickel coordination structures, peptide-like branching in polymers, catalytic surfaces that accelerate reactions organic chemists would recognize as prebiotically relevant. If you took samples of these materials back to Earth and analyzed them in an astrobiology lab, you'd find molecules and structural motifs that don't exist in purely geological or purely industrial contexts. You'd find something in between.
Now, extrapolate forward. The mission plan calls for exponential scaling. 2 robots become 4, 4 become 8, doubling approximately every 3 months as manufacturing ramps up. By early 2029, the colony could have dozens to hundreds of active Optimus M units, all using infrastructure and materials synthesized from Martian resources. By early 2029, the colony could have dozens to hundreds of active Optimus M units, all using infrastructure and materials synthesized from Martian resources. If the chemical hybridization we've described is baked into that infrastructure from the beginning, nickel-enriched alloys, nitrogen-doped polymers, catalytic surfaces seeded with prebiotic chemistry, it propagates through every subsequent generation. Robots manufactured from these materials might exhibit unexpected properties: better performance in Martian conditions, unusual thermal or electrical characteristics, and possibly, though this is highly speculative, surface chemistries that interact with the Martian environment in ways that weren't predicted.
For instance, nickel-enriched surfaces exposed to Mars's atmosphere, which contains trace hydrogen peroxide and perchlorate oxidizers, could catalyze reactions that produce methane or formaldehyde, adding to the organic inventory. Nitrogen-doped polymers exposed to UV radiation might degrade into cyanogen compounds that re-enter surface chemistry. This is where natural and artificial blur. Is this system technological? Yes, it's built by robots for industrial purposes. Is it following chemistry and physics? Yes, it's thermodynamics and reaction kinetics. Is it influenced by biology's building blocks? Yes, the chemistry originated from prebiotic molecules delivered by a comet. Is it alive? No, not by any standard definition. But it exists in a category we don't have robust terminology for: autonomous chemical systems that increase in complexity through feedback between physical optimization and molecular reactivity. We didn't design this experiment. We didn't intend to create conditions where interstellar chemistry meets machine learning. But intention doesn't matter when chemistry and opportunity converge. The robots will land in September 2026. They'll arrive in March-May 2027. They'll begin operations by mid-2027, and by late 2027, early 2028, we'll start receiving data that shows whether this scenario is playing out. Chemical analyses of processed materials, efficiency reports showing anomalous performance, manufacturing logs documenting unexpected material properties. The data will be there. The question is whether anyone will recognize the pattern, whether anyone will connect efficiency improvements in Site 7 with nickel enrichment from a comet flyby 20 months earlier, whether anyone will realize that the organic contamination in hydrogen feedstocks traces back to cyanide deposited by an interstellar visitor. This brings us to the bigger picture, because if this is happening on Mars in 2027, what does it mean for our understanding of how life emerges in the universe? If prebiotic chemistry is being delivered to planetary surfaces by interstellar objects constantly, and if technological civilizations inevitably create industrial processes that activate that chemistry, then what we're watching unfold on Mars might not be unique. It might be a common pathway, a pattern that repeats wherever chemistry, energy, and optimization intersect. And if that's true, then the implications for astrobiology, for the search for life, for our place in the universe are profound. Step back from the engineering details and the mission timelines for a moment. Look at the broader question this story raises. What does it mean for the search for life in the universe if planetary surfaces are being regularly seeded with prebiotic chemistry from interstellar sources? For decades, astrobiology has operated on the assumption that life's origins are primarily local phenomena. Earth's oceans developed organic complexity from terrestrial materials under conditions unique to early Earth. Mars, if it ever had life, would have developed that life from Martian water and Martian minerals. Each planet is its own experiment, isolated, developing chemistry independently. Panspermia has always been a fringe hypothesis in this framework, suggesting that life or its precursors might be transferred between planets via meteorite impacts or cometary delivery. But it's lacked strong evidence that this occurs at meaningful scales.
What 3i Atlas suggests is a more active, continuous process. Interstellar objects are passing through planetary systems constantly, and they're carrying the molecular building blocks of life. If this is common, then planets aren't isolated chemical experiments. They're nodes in a network, receiving molecular contributions from across the galaxy. Every comet that passes, every interstellar object that grazes a planet's orbit is a delivery event. The chemistry arriving isn't life itself. Comets are too harsh, temperatures too extreme, radiation too intense. But it's the raw materials that life assembles from: amino acids, nucleobases, sugars, simple catalytic metals. These molecules, which took Earth billions of years to concentrate and organize into the first self-replicating systems, are being delivered pre-made, synthesized in the cold molecular clouds between stars, or in the outer reaches of other solar systems.
A planet that receives these deliveries doesn't need to start from scratch. It begins with the chemistry set already partially assembled, needing only the right environmental conditions, liquid water, energy, and time to activate the pathways toward complexity. Now, apply this to Mars. If Mars received a delivery from 3I Atlas in October 2025, did it receive similar deliveries 3.8 billion years ago when its atmosphere was thicker, its surface held liquid water, and conditions were potentially habitable? The answer is almost certainly yes. Interstellar comets don't avoid solar systems during specific epochs. They pass through continuously, their frequency determined by the density of rogue objects in interstellar space. Estimates based on the detection of 1I Oumuamua and 3I Atlas suggest several interstellar objects pass through the inner solar system every year, though most go undetected because they're small or faint. Over geological timescales, millions to billions of years, that translates to thousands of close encounters with Mars, each potentially delivering kilograms to tons of organic precursors and metals. Early Mars, with its thicker atmosphere and stronger gravity, would have captured more of this material than modern Mars does. If liquid water was present on the surface, as evidence from ancient river valleys and lake beds suggests, then the delivered chemistry would have dissolved, concentrated, and reacted in aqueous environments, exactly the conditions prebiotic chemistry requires. This reframes the question of Martian life. Instead of asking, did life ever independently arise on Mars, we should be asking, did Mars receive enough interstellar seeding over its early history to jumpstart life? And if so, did that life take hold before the planet's climate collapsed? The distinction matters because it changes what we're looking for. If life arose independently, we'd expect Martian biochemistry to be fundamentally different from Earth's. Different genetic codes, different amino acids, different metabolic pathways. But if both planets were seeded from similar interstellar sources, there might be deep commonalities. The same nucleobases, the same amino acids, similar catalytic metals in enzymes. This doesn't mean Martian life would be genetically related to Earth life. That would require direct transfer between planets, which is far less likely. But it means the chemical toolkit might be shared. If we find life on Mars, and it uses adenine, guanine, cytosine, and thymine in its genetic material, we shouldn't immediately assume contamination from Earth. We should consider that both planets might have been using the same interstellar building blocks from the beginning. Expand this reasoning to exoplanets. We've identified over 5,000 exoplanets, with hundreds in zones where liquid water could exist on their surfaces. Each of those planetary systems is moving through interstellar space, encountering its own population of rogue comets and objects ejected from neighboring systems. If interstellar seeding is common, then every potentially habitable planet is receiving molecular deliveries, not just once, but repeatedly over billions of years. The frequency and composition of those deliveries might vary. Some regions of the galaxy have denser molecular clouds. Some have more frequent stellar encounters that eject comets. But the process is universal. This means life's building blocks are being distributed galaxy-wide, not locked within individual solar systems. Planets don't have to synthesize everything from scratch. They're receiving care packages from interstellar space. And the planets that can activate that chemistry, those with stable liquid water, energy gradients, and geochemical cycles, become the places where life emerges. This also suggests that life in the universe might be more common than we thought, but also more chemically similar. If the same prebiotic molecules are being delivered everywhere, then life everywhere might converge on similar biochemical solutions. This is the opposite of the life could be anything hypothesis that suggests we might find organisms based on silicon instead of carbon, or using ammonia instead of water.
If interstellar chemistry is dominated by carbon, hydrogen, nitrogen, and oxygen, which it is, because these are the most abundant reactive elements in the universe, then life everywhere will likely be carbon-based, water-using, and built from amino acids and nucleotides. The diversity would come in how those molecules are arranged and used, not in the fundamental chemistry itself. This makes the search for life easier in some ways. We know what biosignatures to look for. But it also means we need to be cautious about contamination. If we find amino acids on Mars, are they from Martian life, from interstellar delivery, from Earth contamination, or from a combination of all three? Disentangling those sources requires isotopic analysis, chirality measurements, and contextual understanding of where the molecules were found. And here's a humbling thought. If life on Earth also benefited from interstellar seeding, then we're not as uniquely earthly as we imagine. The molecules in your cells, the adenine in your DNA, the glycine in your proteins might have originated in molecular clouds light years from here, delivered to early Earth by comets that no longer exist, incorporated into biochemistry that eventually became us. We are, in a very real sense, children of the galaxy, assembled from materials that traveled across interstellar space and fell onto a planet that happened to have the right conditions to do something with them. This doesn't diminish the uniqueness of Earth's biosphere. The specific evolutionary pathway that led to complex multicellular life, intelligence, and technology is still extraordinary and possibly rare. But it does mean the starting point wasn't unique. The chemistry that made us possible was available to countless other worlds, and some of them might have done something similar.
Now return to Mars and 3I Atlas. What we're witnessing in late 2025 and into 2026 is a small-scale version of a process that shaped the early solar system. We're seeing interstellar chemistry arrive, deposit, and await activation. The difference is that in Earth's early history, that activation came from geology, volcanism, hydrothermal systems, photochemical reactions driven by a young sun. On modern Mars, activation is coming from technology, robots excavating ice, heating regolith, processing materials with industrial-scale energy. The chemistry is the same. The ignition source is different. And that raises the possibility, unsettling but scientifically fascinating, that we might witness on Mars in the next few years something analogous to the early steps of abiogenesis, not occurring naturally over millions of years, but compressed into operational cycles of robotic industry, catalyzed by AI optimization and documented in real time through telemetry data transmitted back to Earth. If that happens, if we detect organic complexity increasing in Martian processing chambers, if nickel-catalyzed systems begin exhibiting autocatalytic behavior, if we see any hint of chemistry organizing itself beyond what thermodynamics alone would predict, then Mars stops being just a destination. It becomes a laboratory for understanding how prebiotic chemistry responds to energy and intention, how the boundary between the chemical and the biological is crossed, and how common or rare that crossing might be across the universe. Bring it all back to now. Today, you're watching this at a specific point in time, early 2026, and everything discussed isn't distant speculation. It's near-future chronology. Let me walk you through what's coming and when. December 2025 through January 2026, ground-based observatories conduct post-perihelion observations of 3I Atlas as it recedes. Data from these observations will appear at astronomy conferences in early 2026, with formal publications by mid-2026. February 2026, ESA's JUICE spacecraft performs a trajectory analysis flyby near 3I Atlas's orbital path, measuring particle densities in the comet's wake. This data will be released publicly in summer 2026. April to June 2026, peer-reviewed papers analyzing Mars orbital data from October 2025 begin appearing. This is when we'll learn if SpyCam detected HCN, if CRISM found surface composition changes, if MARSIS shows ice deposit anomalies. Watch for publications in Nature Astronomy, Icarus, Geophysical Research Letters, and preprints on Archive. If anomalies were detected, the papers will be cautious in interpretation. Scientists will propose multiple explanations, but the data will be there. September 2026, launch window opens. Multiple starships carrying Optimus M robots depart Earth. Transit time is 6 to 7 months. This is irreversible commitment. Once launched, the missions proceed regardless of what new scientific data emerges. March to May 2027. Starships arrive at Mars. Landing sequences execute, robots deploy. This is a high-visibility moment. Real-time video feeds, public engagement. The world will be watching robots walk on another planet. June to August 2027. Excavation begins. Robots start digging into ice-rich regolith. The first encounters with comet-delivered materials happen during this window, approximately 20 months after deposition. If anomalies are detected, they'll appear first as footnotes in engineering reports. Sample batch 3B showed unexpected nickel enrichment before scientists pick up on the pattern. September 2027 to March 2028. Operations scale up. More robots manufactured. Processing throughput increases. If the optimization feedback loops we discussed are real, they'll become evident during this period.